Hi everyone, in this video we'll see how to set up boundary condition for 2D flat modeling using HEC-RAS model. So we already have our grid refined. We already have other inputs. So now we just need to set up the boundary condition. So it's a 2D model, so our boundary condition is a little bit different than whatever we have for 1D model. So at the very downstream, we'll use the same like condition as 1D, like normal depth. That's okay here. So the condition is we need to draw a line from left bank to right bank. So how can we determine if a bank is a left or right? Since the flow is coming from upstream, so that's the upstream and it's flowing this way. So if you just look at the downstream side, so the left will be the left bank and the right will be the right bank. So that's the left bank and that is the right bank. So we have to draw a line from this side to that side, the same way we cut a cross section in 1D model. So we have a boundary here, and then we have another inflow boundary. So water will come from this side because this is not the headwater uh, basin. So we have another watershed at the very upstream of it. So we need to find a flow here. So flow from upstream basin will give you the inflow to this basin. So we need to somehow determine the flow from the upstream part, and then we need to use that inflow as the boundary here, and then the rest of the boundaries will be out, like overflow boundary condition. We'll just use a normal depth there as well. So let's like start with downstream side. So in order to put the boundary condition, you need to do the same way, like turn the 2D boundary into editing mode and then edit the boundary. So if you click on this, it will be in editing mode, and then select boundary condition line and it will be activated. And if you just select this add new feature, so draw a line outside of the grid, automatically it will snap to the grid and you can see. So it's better to consider a boundary that is uh, covering both 1,000 year if you have the highest profile, or 500 year, so that can contain that boundary. So we can just extend the boundary all the way to this side and then draw a line, and then you can zoom out a little bit, and then you can either, yeah, you can follow like this way, and you can follow this way as well. That's okay for the time being. Double click on it and then it will ask you for the name, so we can put the name as outflow boundary condition. Okay, you can just put outflow BC. That means it's very downstream and you need to use normal depth. So it automatically snap to the boundary and you can see that. So what we need to do, we need to use like overflow boundary. So these are the overflow boundary on the land. Uh, we don't know if flow is coming from this side to that side, or if we have flow from inside to outside. So we need to use the boundary condition here. So we can just do the same way, just draw a line, but the condition is this boundary is already touching this cell. So this cell has already got one boundary condition. So we have to avoid this cell. If you even start from here, that means one cell has two boundaries. So the model will show you error. So to avoid the error, you need to start your boundary here so that it can only touch this boundary. And yeah, I think this is gonna be good. Just roughly try to draw the shape and automatically it will snap. I'm just quickly clicking on it. You don't need to be worried about it. If you just draw the line a little bit away from the mesh, automatically it will snap. You just saw, but it's better to have the boundary closer to the domain. So I'm just clicking and drawing the boundary, following the shape of the study area. And there is no hard or and fast rule to end the boundary, but it's always better to have multiple boundaries. If you see some feature You can just end your boundary here and then you need to start the same boundary, but it will be another part. So it's better for this case, I'm just using the same boundary and I'll use one slope there as well. Yeah, that's why I'm not ending, but you can end it here. I'm just ending where I have another boundary. Another boundary means different types of boundary. Here we have inflow boundary. So that's going to be a discharge boundary. And this one is overflow, means it is normal depth here. So we can end this boundary here, then just use overflow. Overflow BC1 because we'll have the same name but with different number. So we have this boundary, then just draw the same way from left to right. So that's the left bank, that's the right bank for inflow. So we can just draw the line starting from here, and I can just end the boundary all the way to this location and see this is inflow. Inflow BC, we have only one inflow, so we can just use inflow BC and make sure that we have different cells. So this cell is basically missing. It doesn't have any boundary. So what we can do, we can change our create feature or add feature to edit. You can just double click on it and you can extend this one all the way to this, and you can just finish it here. Yeah. So now each cell has one boundary. That means we're done with this, and then we can even extend the boundary from here to the other side as well. Just zoom in to start and change your cursor to add feature mode, and then just draw it pretty quickly, and it'll be done in a minute. So after that, we have to generate our plan. To generate plan, we need to calculate some model parameter like the covariant number, computational time, based on the nominal or minimum size of the mesh. So we'll do that. I have a document. I'll show you the document and then I'll show you how to calculate those numbers using the equations. You can find the equations from the manual. That's okay. Yeah, I'm thinking this is a very large boundary, so I can end it there. And I can just start another one to demonstrate that, okay, we could have multiple boundaries. Yeah, I'm gonna end it on the other side. Just do it pretty quickly, that's okay. Yeah, I can end it here. So before ending, I can end it there. So that the ridge line I can see. So I'm just ending here to capture that cell, and I can just use 2 here, boundary condition 2. I can copy so that I can use it later on. And I can remember that, okay, I already have overflow BC2. So I can, so this cell is already touching this one. So I can start it from here. Yeah, and then just go quickly following this boundary, and then yeah, that's okay because we are confining the area computational domain, so our computation will be confined within this domain, and whenever we have this boundary condition, the model will consider those to compute the water surface elevation, velocity, and flow, and we'll have our flood inundation map at the as a result. So this boundary is fixed because we'll use normal depth. However, we'll use flow boundary as a time series, and there will be different flow values with respect to time. So the model run is going to be unsteady. So if you are familiar with steady and unsteady condition, you know that, okay, if the model like hydraulic condition, like flow velocity changes with respect to time, that means it's not even constant, it's not steady, so it's going to be unsteady. So we are gonna run the model for several days because we already created the rainfall data. We distributed the rainfall over 24-hour, and we have 6-minute interval of that grid. We already saw that in the previous videos. That means we have different values with respect to time, and it's going to be unsteady condition, so that has to be correct as well. And I'm just ending it here because this cell is empty. If I double click, it's done. So that is my overflow BC number 3. So that's it. If I zoom out, and I can show you like the model is contained. So what I can do, I can click stop editing, and then my edit is done. So it's setting the boundary. So that's my model boundary we have. If you want to show that, okay, from layer properties, you can label that, go to edit, and there will be a name, and you can show the name as well. And you can see which boundary is which. So that's inflow we see, that is basically outflow, and these are the overflow boundary. So this overflow boundary condition, we can use normal depth as 0.005, but for outflow BC, we need to calculate or estimate. So how can we estimate that normal depth here, the slope? Basically, that has to be from water surface elevation, but we can use the terrain, the DEM we have here, and we can just use our measure tool, and then we can just take the average. Like if you draw this line following the deepest part, we call it Thalweg, and if you just go a little bit upstream and double click, it will give you the length, and at the same time it is giving you the slope as well. So that's the slope, 0.003138. So this is the slope we're going to use here as the boundary condition. And for overflow boundary here, we're just gonna use 0.005. So we have different boundary conditions for outflow and for overflow as well. And we need another one here, inflow, but we need to calculate that as time series. So for the sake of running the model for the first time, we're not gonna use that boundary. We'll use that as 0 value, and then later on we'll estimate, and I'll share with you how can we estimate the value. Because we don't have any gaze, we need to look for the gazes as well, and we need to look for even a dam as well. If we have different dams, we need to restrict or detain flow or water for different purposes. It could be for recreational, it could be for flood control, or it could be for fire protection. So we need to know the purpose, and we need to know the owner. So if the owner is the government or US Army or the federal people, then and the purpose, if the purpose is for flood control, then we need to treat the dam in a different way. We need to find a rating curve or rule curve for the dam, so we can use either 2D connection or different things. So we don't have that big dam, but we'll download the data from National Inventory of Dam, NID, and we'll just show how many dams we have within this study area, and then we can zoom in and we can add a break line. We'll do that later on after running the model for the first time. We can see. So we're done with the boundary condition. We can save it, and then we can go to the main window of the model, and we need to insert that boundary condition, right? So let me just go to edit. Since it is unsteady, we can go to unsteady flow, and here we don't have any boundary. So what we need to do, because we didn't even import that geometry into the geometry editor, so click on that editor. So that RAS mapper is still open and it's in editing mode probably. Let me show you which one is in editing mode, or it's a different one. Okay, so I'm just going to cancel. So now let's go back and open unsteady flow. Okay, we need to go to that geometry editor. There is no geometry because we didn't add it or we didn't create. So go to open geometry, and we have this 2D geometry. We can just import it. So that's the computational domain, and we have this mesh, and you can save the geometry and you can close it. and you can see that we have the geometry. So now we need to create the plan. We need to edit the unsteady flow because we previously added the gradient precipitation, but now we just added our boundary. So now we can see different boundaries here. So BC1, overflow BC1, so we can use normal depth. And I already mentioned that we'll use 0.005 as the normal depth for overflow. So this is also inflow. We need to use flow hydrograph, and we'll do that later on. We'll add values, but we'll add 0 now. And we have another overflow boundary condition. Then we can just use 0.005. So this is another one. We can use normal depth as well. We can use 0.005. And we have outflow BC. We can use normal depth, but this time the one we measured, it's 0.003138. So that's the boundary at the very downstream. So here we need to add the flow boundary, but we need to specify the simulation time. So if you can remember, the simulation time has to be synchronized with the rainfall data. So for the rainfall data, what we used, we can even see that. Let me save the unsteady flow we just added. It's saved, and if you go to event here, you can see that access to DSS file, and you can see the rainfall data imported into the model. And if you want to check the DSS file, you can click on that DSS view, and you can see your all the profiles from DSS file. So we just added 1%, means 100-year return period. So that 1%, it's starting from 28th of July 2024. So that is going to be our run condition. 28th of July 2024. Yeah. So what I can do, I can close it. Okay, now let's generate the plan first, because we need to assign the time, and then we can add 0 value to the inflow boundary condition, because inflow boundary has to be synchronized with the run condition as well. So go to run and unsteady flow analysis. It's empty now, so we need to create a new plan. So we need to turn on this geometry preprocessor, because it will check if the geometry is okay or not in terms of the cell size and shape and everything. And then it will do the unsteady flow simulation, and it will do also the post processor thing, and then it will also just generate flat plane mapping, but that's not mandatory. And if you want, yeah, you can just add your time, like the same time, 2024, and it was, I think, July 28th. So that was the day, July 28th. We can add, and here we can just end it up to, we can use July 30. That's okay. And the starting time has to be at 00 hour. That's okay. And computational interval. So we have to specify this computational interval here. That's the starting time. But for time series, you can use 1 hour, you can use 15 minutes. So we can just use 5 minutes. So that is going to be our time series data. And for mapping output, we'll have 1 hour. After 1 hour, it will just generate one map. That's also okay. And detailed output interval, it's going to be 1 hour. That's also okay for the sake of running the model. And then go to file and save the plan. And since we are saving the plan for the first time, we can use a title called 1%, because we are running the model for 100 years, which is 1% chance of occurring the event in a year. So 1 PCT, that's okay. We can use 1 PCT. I'm just giving the short name. And here we can use the same one PCT. So our simulation is ready starting from 28th of July. This is the plan, and we can see short ID and long ID. You can save the plan, but if you try to run the model, it won't run because we are not done with the unsteady flow data, because we still have to use that inflow boundary condition here. So starting from July 28, 00 hour, and if you just use 1 hour data for the sake of running, how many ordinate we'll have. So we're running the model up to July. Yeah, we can just create that 0 time series, and later on, we can generate the real case. So I'm just opening an Excel file, and then let me create a 0. So first one is going to be July. So 07/28/2024. And if I just use 0000 hour, and let's see if it is going to give us this time. But now, so this is going to be not 00. We're gonna create a time series. It's going to be same, but we need to use this as 1. Okay, 01. And maybe it will follow if you just drag. Let me check. Yeah, 9, 12, 13, 24, and yeah, it's changing. So you can go all the way, and you have July 28, 29, yeah, 10 hour. Yeah, maybe we just need to click here. July 28 is done, July 29, then July 30, 31. Okay, that's okay. So we can just use 0, and all will be 0, and I can just copy, and I can fill this up because we need to use here the data set, and we can plot to see script is out of range, means we may have, okay, we don't have this data. We have the data, but we don't have time. The July 31st is okay. We can just delete because our ordinate is up to 100. That's the reason. Yeah, we have 0. It's plotting 0 if you have any data, so it will just plot. Later on, we'll plot it, but for the sake of running, so we can use the slope here, BC 0001. Now I'm just saving it. That's okay. I can just go to file and save the unsteady flow data. That is also done. So what else we need? We need to set up some other conditions as well. We need to set up this computational time. So let me open a document I have. So here is the document. For any model, you need to set up the initial condition. There are multiple ways to set up the initial condition but for this case, we're not going to use it, but you can just use several days or several hours for spin up time, and you can use previous model as restart file. So these are the conditions I just mentioned here, but the main thing is we need to calculate the computational time. So our mesh, this is the equation. We need to use the cell size, nominal cell size in feet. And if you use this equation, you'll get the time step in second. So our case, we saw like we have 200 feet by 200 feet as the maximum cell size, and then we refined it. So we need to, that's the maximum and that's the minimum. So if you use this 200, so you'll get 30 second, and we have here 12 second. So we can use 30 second. And that's the input is going to be 30 second based on the cell size. We can save the plan. What else we need? So let's go back to the document and see we need to use adaptive time step. So from unsteady flow computational option, if we go there, so maximum current number has to be 1.5, and then minimum will be 0.45. The number of steps below minimum before doubling is 5, and then we have maximum number of doubling base time is 2 minutes, basically 120 second, and then we have maximum number of halving base time is basically 2. So we can just change this condition. I'm just putting it on the other side of the window, and just let me find that. If you go to options, and you can see computation option and tolerances, and you will find all those values like advanced time step. So here you just need to select this option instead of fixed, then it will automatically change your time step based on the cell size and the current number, right? The maximum is 1.5 and the minimum is going to be 0.45, because there is a rule, your current number has to be maximum this, but so that's the limit. It has to be less than 0.5. The minimum is going to be maximum current number divided by 2, but it has to be less than 0.5. So we are using 0.45. And then this is going to be 5. This is 2 minute, 120 seconds, and this is going to be 2. Okay, so we can just click OK, and we can save it. We can save the plan, and our model is ready to run. We don't have anything. We just added our boundary condition, but we need to still use the inflow boundary condition from the either from gaze analysis or from another model. So we'll check and we'll see that. So we are running the model for this time step. We already have our data, so let's run. It will check the geometry first, and then it will do. Okay, let me just run the model. And if we are good at all the inputs, then it will run. Yeah, it's checking the geometry. It will take a while. There are 4 steps. It may take a long time for millions of cells, but it will check all 4 conditions, and then if everything is okay, then it will go to the next step, and then it will show you, see, these are yeah, this warning. So that's okay. So it is going to run, and it started running the model. Maybe it will take a while, because you can see it started with July 28th, and here you can see the iteration. So I'm just trying to pause the video, and whenever it will be done, so I can share with you the result, and later on we'll just improve our model. So just I'm pausing the video right now, and I'll come back. Yeah, the simulation is done successfully, so we can check the result. If you want to see the result, you have to click on the result, and you can see that plan 1%. If you just turn it on, and you have depth, velocity, and water surface elevation. If you want to see the depth, click on the depth, and it's giving you the maximum depth. And here we can see the depth of the water, like at every location. These are basically from rainfall. We used rain on grid, so it's basically generating the depth from the rainfall. We didn't even add anything from upstream, but here you can see if water is connecting or storing anywhere. We need to investigate all those things. If it is following the streams, and you can see the deep portion, and then we need to calibrate. If you zoom in every locations, here we added a cut line, right? And then we can see the connectivity in between upstream and downstream of any culvert or a structure. Yeah, if I turn on the break line, we can see where we should have, yeah, our culverts. So this is how we can see the result. This is basically the maximum depth. And if you want to see the animation, still you can do that. You have the option here. You can drag that on this side, and you can just play it, and you can see at the, yeah, very quickly you saw that. So that's that. So we have to improve the model now. We need to even calibrate the model. We can do that in the future videos. We'll do that. We'll complete the entire modeling, and we can generate the flood inundation map. So that's that. I'm gonna end the video here, and then you can try. And if you have any question, you can ask me. I'll try to answer your question. And thank you for watching, and stay safe.